Welcome, viewers, to another exciting class. Today we are still on thermodynamic relation and we are going to be solving the above question. Now we are asked to find the expression for the S, that is the change in entropy, in terms of the change in temperature and change in pressure. Now let's dive into it. First, before we go, we are going to let S to be, which is entropy, to be a function of temperature and pressure, because we are asked to express the S in terms of temperature, in terms of the change in temperature and change in pressure. So let's go. So we will let S to be a function of temperature and pressure. Now, from our basic law, of course, on the fundamentals of partial derivative, the S can be written as the partial derivative of S all over the partial derivative of t, keeping p constant the t, plus the partial derivative of S all over the partial derivative of p, keeping t constant the p. So this is what we have. So next, we are going to be using Maxwell relations. Now, for our Maxwell relations, we know that from Maxwell relation, we know that the partial derivative of S all over the partial derivative of p, keeping t constant, is equal to minus the partial derivative of v all over the partial derivative of t, keeping p constant. Now, from our Maxwell relation, we have this as one of its relations. So next, if you look at this equation very well, you can see that what is here is equal to what is here. So what we are going to be doing is very simple. We are going to be substituting the value of this, which is this, in this above equation. If we do that, the S will be equal to, we have the partial derivative of S all over the partial derivative of t, keeping p constant, the t. Now we are substituting this value here. So it means we are going to be having minus the partial derivative of v all over the partial derivative of t, keeping p constant. Yes, keeping p constant, dp. So this is what we have. Now we know that the H, which is our change in enthalpy, is nothing but Cp dt. We know that the H is nothing but Cp dt. We also know that the H, we also know that this equation is equal to Tds plus v dp. From our first lecture, we are proving this. This is not a partial derivative. This is H, which is the change in enthalpy, is equal to this. We have H to be equal to this, and it's also equal to this. So from here, we can make dt. We can divide through this equation by dt. Dividing this equation by dt and keeping pressure constant, it implies that I have Cp dt to be equal to Tds plus v dp. If I divide through this equation by dt, keeping p constant. If I say keeping p constant, it implies that the p here automatically becomes 0, and this equation automatically becomes 0. So what I'm going to be having is Cp. From here, you know that the t can go with the t. So I'm going to be having Cp to be equal to t into the partial derivative of s all over the partial derivative of t in order to keep p constant. So this is what I am going to be having. Now, if you look at this equation, what we have here is equal to what we have here. So what I'm going to be doing is that I'm going to be making this the subject of this relation and then substituting its value in the above equation. If I do that, I'm going to be dividing through this equation by t. If I divide this equation by t, t here can go with t here. If we take the inverse, it implies that this will be equal to, I'm going to have Cp all over t to be equal to the s all over the t, keeping p constant. This is what I am going to have. So I'm going to substitute this for this in this equation. So if I do that, the s will be equal to Cp all over t dt. minus dv all over dt, keeping p constant, dp. So this is what I am going to have. This is what I am going to have. I can rewrite this equation by saying the s is equals to cp dt all over t minus dv all over dt, keeping p constant, dp. Of course, these two equations are the same thing. I just took t to this side, they are multiplication, so they are the same. Now, from our previous video, we know that the coefficient of volume expansion, which is denoted by beta, we know that beta, which is our coefficient of volume expansion, is equal to 1 all over volume into the partial derivative of v all over the partial derivative of t, keeping p constant. We know that beta is equal to this. If I multiply this equation by volume, I'm going to have volume multiplied by beta to be equal to the partial derivative of v over the partial derivative of t, keeping p constant. Of course, volume, which I've multiplied by this, we cancel this, and so we'll be having volume here only. So next, if you look at this equation, you can see that what is here is of course the same with what is here. So I can substitute this value for this equation. If I do that, I can substitute this value for this equation here, but we are going to be working with this, so I'm going to be substituting this value for this in this equation. If I do that, I'm going to have the s to be equal to cp dt all over t minus v beta delta p. So this is what I'm going to have. So this equation is the expression for the s in terms of the t and in terms of the p. So we have the t here and we have the p here. So we have successfully found the expression for the s in terms of the t and the p. So thank you for watching, and stay tuned for more videos.